This is a dramatic reading of Snarky Puzzle Answers 3, a blog by the Stand-Up Physicist, available at science20.com. The key to getting lots of reads of a blog is a good title. Now, for my blogs, the ones that had the fewest number of reads were Snarky Puzzle Answers and Snarky Puzzle Answers 2. Do I have high hopes for SPA 3, Return of the Nerds? No. I expect the community to be consistent. And this is really just more an observation than a complaint. Now, what's really exciting me, though, is that I'm still asking questions and developing answers. I want to emphasize the plural. This is not a one-trick pony. Oh look, quaternions can do 3D rotations, and that's about it. No, many different topics are being raised and looked at a funny angle. I didn't actually have a plan to write out these puzzles, but I'm glad that it emerged from the blogging process. And so now let's get back to some actual questions and their answers. On May 24th, we had Argand plane crash. And here was the snarky puzzle at the end of that blog. Ever lasts only until a counter example is found. A circle in a complex plane has so much space-time symmetry. It comes out as it goes in, and there are always 2 points. Discuss how you can find the origin, the when, and the where it is. So here's the backstory. Circles are just so central to our experience, let alone physics. I mean, we were raised drawing circles in a Euclidean plane. To animate such a familiar thing, you'd actually make a cylinder in space-time, and then time wouldn't be doing anything of interest because it's static. Now, the best field theory we have is the Maxwell equations. The symmetry that goes hand in hand with electric charge conservation is known as the unitary group big U1, the complex numbers with a norm of 1. Its Lie algebra small u1 needs only one complex number to do its job. Now, time, what you do is you take time squared plus space squared, and that equals 1. It's simple as that. Except our lives are lived linearly in time. Squaring time is outside of our own experience. Now, a computer can do this easily enough. So here's the answer. What I needed was a little bit of algebra, shown right there. So what we're doing is we're taking just any old random quaternion, and we're subtracting from it I times that random quaternion times I, and then taking its norm. And this actually ends up giving you just AB over its norm, a squared plus b squared. And just plot away, and that's what you get. So there are 2 spheres on the screen at all times, a sign of spatial symmetry. The spheres end as they started, a sign of time symmetry. When the 2 spheres are farthest apart, that marks the time t equals 0, or now. The spatial origin is always halfway between the 2 spheres. Note how the complex plane circle is a circle only in that bottom center one, which is right, left, plus time complex plane. Let's see if this description is valid if the circle is given a Lorentz boost along the x-axis. Well, this no longer looks like a circle of the complex plane. One can still pinpoint the origin as before. Time zero happens when the points are farthest apart, and the spatial origin will be halfway between the points at that moment. Spatial symmetry is preserved if one moves the mirror along with these 2 points, which is actually what would happen in a Lorentz boost. Time symmetry is broken, though, because the animation, when it ends, is not where it is when it begins. So let's look at a boost along the y-axis. The circle becomes an ellipse because time gets stretched out by the boost. Time symmetry is again broken. The spatial symmetry, though, is preserved. You can see those 2 dots. The discussion. They say over in Wikipedia land that the unitary group can be viewed as the intersection of 3 sorts of groups: the orthogonal, the symplectic, and the complex groups. And this actually just boils down to these statements right here. Okay, we got that. All right, great. So we've got the transpose times some other guy times that A gets you back to where you started. Or if the complex, you've got the inverse of A times J times A gives you J. And the orthogonal, you're going to have the transpose equaling the inverse. Now, what they say is that if you have 2 of these guys, then you have the third. It's kind of nice. Now, when you do this with quaternions, if you get 1 of those, then you get the other 2. Now, take, for example, the symplectic group. Because quaternions are what's known as a normed division algebra. So that means that here the norm of A times the norm of J times the norm of A is the same as multiplying all those guys out and then taking the norm. So the only way that could work out is if the norm of A is equal to 1. Now, a quaternion inverse is the transpose over the norm. Well, the norm was 1. So of course, orthogonality is satisfied. You know, you got the transpose equaling the inverse because the norm is 1. And the complex thing is going to also follow suit because now the transpose is, you know, so basically you get 1. With quaternions, you get all 3. And that's all there is to it. On May 30th, I had a post called Why Quantum Mechanics is Weird. And here was my snarky puzzle. Complex analysis is a gold mine of important ideas. Quaternion analysis is a barren moonscape. The best work to date was done in the 30s, and that was unable to show that Q squared was actually analytic in Q. Dead end city. So grab a polynomial by the horns, show that Q star squared is analytic in Q star. Bonus points if you can do that proof 5 different ways. So here's the backstory. At my first international conference in Rome in 1999, yes, the second guy to speak was, and that, by the way, means he's very important, started to talk about quaternion analysis. And he described the problem brilliantly. Well, he's from Oxford after all. No. And I was actually getting really excited because the ability to do quaternion analysis is absolutely vital to any robust assault on the accounting system of physics. And he just started to describe his own approach to solving this problem, and it used left-hand derivatives. And I thought, yuck. And he kept on going on about this, and I was getting madder and madder. And I mean, this is really an odd reaction to have to a math professor from Oxford. Oh my God, they're a level above Harvard. I mean, that's something. But his approach struck me as just so terrible that I decided to try and devise a decent quaternion derivative definition. So here's the answer. There are probably at least 5 different ways to show a complex valued function is analytic or regular or holographic, something like that. You know, I can only remember 3 of these ways. The chain rule, Cauchy-Riemann equations, and the holonomic equation. And since this is really serious technical math stuff, and I work out of this isolation chamber that is my basement, please be gentle if my descriptions are just a little bit imprecise here. But I mean, I think I'm actually focused on something called holomorphic functions. These are complex valued functions that are equal to their Taylor series at every point in their domain. And I'm actually going to skip answering the question. So, why? Well, here's my discussion of why I did that. I mean, a big thing really happened in the due to comments from David Halliday. When I realized that norm stuff that I'd been thinking about for like more than a decade was superfluous. What was still vital is the multiple limits. And David's actually trying to talk me out of those too, but no, the logic there still sounds good to my ear because quaternions don't commute. So how do you deal with that? You say problem children go to 0. And then I don't have any problem children, so things work out. I mean, that logic still feels good to me. But David's skeptical of the entire approach. Now, skepticism is a good thing, okay? But he has shaken my confidence in this topic. So please take my work with a large block of salt. In fact, consider it not worth your time worrying about until I come back with another blog on the subject. The blog will have to have an accompanying Mathematica notebook. And what I hope to show, and of course I might not be able to do so, is how the single limit definition is broken, but that my more than one limit thing works better. Now, if I can get that bit of algebra working, then I can apply it to a whole bunch of variations in multiple limit processes. And from there, I'm going to have to travel down the road through the Cauchy-Riemann, the chain rule, the holonomic sort of thing, for all those variations and whatnot. It's very specific, it's very concrete. It might be doable. We'll find out in the future! Alright, well, on June 7th, I had a blog entitled Constructing Consistent Linear Field Equations for Gravity. And here was my snarky puzzle. Write out the Maxwell equations in the Lorentz gauge. Write out the hypercomplex gravity equations in the Lorentz gauge. Subtract the first equations from the second, shop and compare that with the GEM unified field equations, actually which are on this t-shirt, and reflect on how important it is to be similar but not quite the same. As Jan used to say on the Brady Bunch, Gage, 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 why does Gage get all this attention? Well, there are entire books on the subject that have not really made it to my summer reading list because they tend to be too heavy to take to the beach. Lagrange densities need to be invariant under a gauge transformation so that particles can zip along at the speed of light. Good for them. But field equations that result from applying the Euler-Lagrange equations to that density usually end up depending on your gauge choice. And I just don't have a broad enough exposure to know if that usually should read like always. Alright, so here is my answer. Okay, we can get that up on the screen. Nice and close. Okay, so the top line, that's max. Then there's my hyper complex guys with a plus in there. And if you subtract one from the other, you lose your time dependent guy. Oh, you also lose the current density. That's kind of crazy. So here's my discussion of this napkin. You know, I nibbled on a few pages of Michael Kukau's Quantum Field Theory, a Modern Introduction, a 750 plus page book on the subject. And one quote actually stuck with me through the years. In section 4.3, quantizing the Maxwell field equations, page 106 in your hymnal. The problem with this operator is that, and it was having to do with the Maxwell equations, is that it's not invertible. And hence, we cannot construct a propagator for the theory. In fact, this is typical of any gauge theory, not just Maxwell's theory. This also occurs for general relativity and in superstring theory. Okay, so does the gem Lagrangian get around this common plague? I mean, the field equations don't change if you choose the Coulomb gauge, or the Lorentz gauge, or the Feynman gauge, or just any old gauge. This might actually be a critical difference. At least, I'm hoping! Alright, now on June 14th, I had the Gamma Girl graphs. And here was my Snarky puzzle. Well, this is actually a Snarky puzzle mystery, because I usually know the answer. Well, this time I don't. That might make writing the answer more difficult for me, but I doubt you care. I went way out on a limb to embrace something I call the California numbers. Being from the East Coast, I do have some troubles doing that. I mean, I have a friend who lives out on that way out west coast, and he's into the barefoot running revival, you know, wearing these shoes that have individual places for each toe. I mean, now in this blog, I generated some California number multiplication graphs using only quaternions. Now see if numerically you can show that the two are the same, the California numbers or these quaternion triple products. Now if that can be done, I can stay on the East Coast with the division algebra known as quaternions. So the backstory is that I built a Klein pipe cleaner model of quaternions. And actually, why don't I just go get it? It's right over here. That's why you keep it around. You know what I'm saying? And there it is. Right there. Kind of nice. Okay. And I also built one for the California numbers. And look like that. And you see, we went from two pipe cleaners, which were directional, to this one, which they're not directional anymore. So that was really great. The clarity of the difference, I really like that. But I can just guarantee you that the California numbers, what's there, well, the pipe cleaner thing, and what came up with the gamma graphs, where I did things like 1Q1, IQI, JQJ, and KQK, they're not the same. They just aren't. Okay? And the reason is that the Klein 4 group has 6 edges, but that only 3 of the labels are distinct. In other words, you know, they've got the same... Oh, I know. I can show it. See, there's an I right there, and there's an I right there. There's a K and a K and a J and a J. Exactly the same. Now, when I did the gamma matrices, these guys, these three around here at the base, they were all the same. These guys were all minuses, okay? And those minuses means they have 6 distinct labels, and so they're just different animals. I mean, there's nothing more complicated than that. But I wanted to know what to call this distinct thing, so I went over to a place called math.stackexchange.com and asked my question, and they said, that sounds like a Cayley graph. Now, I've never actually worked with the Cayley graphs before, so I will let my readers or viewers investigate that sort of subject on their own. I do have the Cayley graph table. What do we call this? This Cayley table for the Klein 4 group up there, and you can see the differences that in this lower kind of quadrant there's some minus signs, and those make a difference. Now, is this going to have some real simplifying properties? Don't know. It's an area that's open for research. That's what I said. But I know they're different, and that was the nature of the question. So that's the answer. Thank you very much.